In this video, I'd like to start adapting support vector machines in order to develop complex nonlinear classifiers. The main technique for doing that is something called kernels. Let's see what these kernels are and how to use them. If you have a training set that looks like this, and you want to find a nonlinear decision boundary to distinguish the positive and negative examples, maybe a decision boundary that looks like that, one way to do so is to come up with a set of complex polynomial features, right? So a set of features that looks like this, so that you end up with a hypothesis X that predicts 1 if, that theta 0 plus theta 1 x1 plus dot dot dot, all those polynomial features is greater than 0, and predicts 0 otherwise. And another way of writing this, to introduce a little bit of new notation that I'll use later, is that we can think of a hypothesis as computing a decision boundary using this, so theta 0 plus theta 1 f1 plus theta 2 f2 plus theta 3 f3 plus and so on, where I'm going to use this new notation f1, f2, f3 and so on to denote these new sort of features that I'm computing. So f1 is just equal to x1, f2 is equal to x2, f3 is equal to this thing here, so x1, x2, f4 is equal to x1 squared, f5 is equal to x2 squared, and so on. And we've seen previously that coming up with these high order polynomials is one way to come up with lots more features, but the question is there a different choice of features, or is there a better choice of features than these high-order polynomials? Because, it's not clear that these high-order polynomials is what we want, and when we talked about computer vision, talked about when the input is an image with lots of pixels, we also saw how using high-order polynomials becomes very computationally expensive, because there are a lot of these high-order polynomial terms. So is there a different or a better choice of the features that we can use to plug into this sort of hypothesis form? So here's one idea for how to define new features f1, f2, f3. On this slide, I'm going to define only 3 new features, but for real problems, we're going to define a much larger number. But here's what I'm going to do. In this space of features, x1, x2, and I'm going to leave x0 out of this, the intercept term x0, but in this space, x1, x2, I'm going to just, manually pick a few points. I'm going to call this point L1. I'm going to pick a different point. Let's call that L2, and let's pick a third one. I'm going to call this one L3. And for now, let's just say that I'm going to choose these 3 points manually. I'm going to call these 3 points landmarks. So landmark 1, 2, 3. What I'm going to do is define my new features as follows. Given an example X, let me define my first feature, F1, to be some measure of the similarity between my training example X and my first landmark. And the specific formula that I'm going to use to measure similarity is going to be this, is e to the minus the length of x minus L1 squared divided by 2 sigma squared. So depending on whether or not you watched the previous optional video, this notation, this notation, right, this is the length of the vector w, and so this thing here, this x minus L1, this is actually just the Euclidean distance, squared, is the Euclidean distance between the point x and the landmark L1. I'll say more about this later. But that's my first feature, and my second feature, F2, is going to be similarity function that measures how similar x is to L2, and again is going to be defined as the following function. So it's e to the minus of the square of the Euclidean distance between x and the second landmark. That's what that numerator is, and then divided by 2 sigma squared. And similarly, F3 is similarity between x and L3, which is equal to, again, similar formula. And what this similarity function is, the mathematical term for this is that this is going to be a kernel function. And the specific kernel that I'm using here, this is actually called a Gaussian kernel. And so this formula, this particular choice of similarity function is called a Gaussian kernel. But the way the terminology goes is that, in the abstract, these different similarity functions are called kernels, and we can have different similarity functions. And the specific example I'm giving here is called a Gaussian kernel. We'll see other examples of other kernels, but for now, just think of these as similarity functions. And so instead of writing similarity between x and L, sometimes we'll also write this as a kernel denoted, lowercase k between x and one of my landmarks Li. So let's see what these kernels actually do, and why these sorts of similarity functions, why these e to the so on expressions might make sense. So let's take my first landmark, my landmark L1, which is one of those points I chose on my figure just now. So the similarity of the kernel between x and L1 is given by this expression. Just to make sure we're all on the same page about what the numerator term is, the numerator can also be written as a sum from j equals 1 through n of sort of the distance. So this is the component-wise distance between the vector x and the vector L. And again, for the purpose of these slides, I'm ignoring x0, so just ignoring the intercept term x0, which is always equal to 1. So this is how you compute the kernel, or the similarity between x and a landmark. So let's see what this function does. Suppose x is close to one of the landmarks. Then this Euclidean distance formula in the numerator will be close to 0, right? So that is this term here, the distance, or the square distance between x and L will be close to 0. And so f1, this feature will be approximately e to the minus 0 in the numerator squared over 2 sigma squared. So then e to the 0, e to the minus 0, e to the 0 is going to be close to 1. Okay, and I put the approximation symbol here because, the distance may not be exactly 0, but if x is close to the landmark, this term will be close to 0, and so f1 will be close to 1. Conversely, if x is far from L1, then this first feature, f1, will be e to the minus of some large number squared divided by 2 sigma squared, and e to the minus of a large number is going to be close to 0. So what these features do is they measure how similar x is from one of your landmarks, and the feature f is going to be close to 1 when x is close to your landmark, and it's going to be 0 or close to 0 when x is far from your landmark. And each of these landmarks, on the previous slide I drew 3 landmarks, L1, L2, L3. Each of these landmarks defines a new feature, F1, F2, F3. That is, given a training example x, we can now compute 3 new features, F1, F2, F3, given the 3 landmarks that I wrote out just now. But first, let's look at this exponentiation function. Let's look at the similarity function and plot it in figures and just understand better what this really looks like. For this example, let's say I have 2 features, x1 and x2, and let's say my first landmark L1 is at a location 3, 5. So, and let's say I set sigma squared equals 1 for now. If I plot what this feature looks like, what I get is this figure. So the vertical axis, the height of the surface, is the value of f1, and down here on the horizontal axes are, if I have some training example, and that's x1 and that's x2, given a certain training example, if I have a training example here for a certain value of x1, x2, right, the height above the surface shows the corresponding value of f1. And down below is the same figure shown using a contour plot with x1 on the horizontal axis, x2 on the horizontal axis, and so this figure on the bottom is just a contour plot of this 3D surface. You notice that when x is equal to 3, 5 exactly, then the f1 takes on the value 1 because that's at its maximum, and as x moves away, as x goes further away, then this feature takes on values that are close to 0. And so this is really a feature, f1 measures how close x is to the first landmark, and it varies between 0 and 1 depending on how close x is to the first landmark L1. Now, the other thing I want to do on this slide is show the effects of varying this parameter sigma squared. So sigma squared is a parameter of the Gaussian kernel, and as you vary it, you get slightly different effects. Let's set sigma squared to be equal to 0.5 and see what we get. If we set sigma squared to 0.5, what you find is that the kernel looks similar, except that the width of this bump becomes narrower. The contours shrink a bit too. So if sigma squared equals 0.5, then as you start from x equals 3,5, and as you move away, then the feature f1 falls to 0 much more rapidly. And conversely, if you were to increase sigma squared, so here I've set sigma squared equals 3, in that case, as I move away from L, so this point here is really L, right? As L1 is at location 3, 5, right? So shown up here. And if sigma squared is large, then as you move away from from L1, the value of the feature falls away much more slowly. So given this definition of the features, let's see what sorts of hypotheses we can learn. Given the training example X, we're going to compute these features f1, f2, f3, and our hypothesis is going to predict 1 when theta 0 plus theta 1 f1 plus theta 2 f2 and so on is greater than or equal to 0. For this particular example, let's say that I've already run a learning algorithm, and let's say that somehow I ended up with these values of the parameters. So theta 0 equals minus 0.5, theta 1 equals 1, theta 2 equals 1, and theta 3 equals 0. And what I want to do is consider what happens if we have a training example that takes that has a location at this magenta dot, right, where I just drew this dot over here. So let's say I have a training example X. What will my hypothesis predict? Well, if I look at this formula, because my training example X is close to L1, we have that F1 is going to be close to 1. But because my training example X is far from L2 and L3, I'll have that, F2 will be close to 0, and F3 will be close to 0. So if I look at that formula, I have theta 0 plus theta 1 times 1 plus theta 2 times some value, not exactly 0, but let's say close to 0, and then plus theta 3 times something close to 0. And this is going to be equal to, plugging in these values now, so that gives minus 0.5 plus 1 times 1, which is 1, and so on, which is equal to 0.5, which is greater than or equal to 0. So at this point, we're going to predict y equals 1, because that's greater than or equal to 0. Now, let's take a different point. Now, let's say I take a different point. I'm going to draw this one in a different color, in cyan, say. For a point out there, if that were my training example X, then if you make a similar computation, you find that f1, f2, f3 are all going to be close to 0. And so we have theta 0 plus theta 1, f1, plus so on. And this will be about equal to minus 0.5, because I guess theta 0 is minus 0.5, and then f1, f2, f3 are all 0. So this will be minus 0.5. This is less than 0. And so at this point out there, we're going to predict y equals 0. And if you do this yourself for a range of different points, you should convince yourself that if you have a training example that's close to L2, say, then at this point, we'll also predict y equals 1. And in fact, what you end up doing is, if you look around this space, what we'll find is that for points near L1 and L2, we end up predicting positive, and for points far away from L1 and L2, that is for points far away from these two landmarks, we end up predicting that the cost is equal to 0. And so what we end up doing is that the decision boundary of this hypothesis will end up looking something like this, where inside this red decision boundary, we predict y equals 1, and outside we predict y equals 0. And so this is how, with this definition of the landmarks and of the kernel function, we can learn a pretty complex nonlinear decision boundary like what I just drew, where we predict positive when we're close to either one of the two landmarks, and we predict negative when we're very far away from any of the landmarks. And so this is part of the idea of kernels and how we use them with a support vector machine, which is that we define these extra features using landmarks and similarity functions to learn more complex nonlinear classifiers. So hopefully that gives you a sense of the idea of kernels and how we can use it to define new features for the support vector machine. But there are a couple questions that we haven't answered yet. One is, how do we get these landmarks? How do we choose these landmarks? And another is, what other similarity functions, if any, can we use other than the one we talked about, which is called the Gaussian kernel? In the next video, we'll give answers to these questions and put everything together to show how support vector machines with kernels can be a very powerful way to learn complex nonlinear functions.